Stokes' law states that for a sphere moving through a fluid, the viscous drag acting on it is given by the equation F equals 6 pi eta RV, provided that the movement of the fluid relative to the sphere is laminar. The Stokes' law equation states that the viscous drag, which is the frictional force from the fluid measured in newtons, is equal to 6 pi times the coefficient of viscosity, which is a measure of the resistance to flow for a fluid in Pascal seconds, times the radius of the sphere in meters, times the terminal velocity, which is the velocity of the sphere when there is no resultant force acting on it and is measured in meters per second. As the sphere travels through the fluid, there are three main forces acting on it. There is the downward force of weight and the upward forces of viscous drag and upthrust. Upthrust is the upward force equal to the weight of the displaced fluid. Just after the sphere enters the fluid, the downward force of weight is greater than the upward forces of upthrust and viscous drag combined. This means there is a resultant force downwards, so the sphere is accelerating downwards, so its velocity is increasing, so terminal velocity has not yet been reached. Therefore, Stokes' law cannot apply here. Over time, the magnitude of the viscous drag increases until the magnitude of the upward forces are equal to that of the weight. This means there is no resultant force, so the velocity of the sphere is constant. So at terminal velocity, the weight is equal to the upthrust plus the viscous drag. Laminar flow happens when adjacent layers of fluid do not cross into each other, causing the velocity of the sphere to remain constant. This means the sphere remains at terminal velocity, so Stokes' law can be used when the flow of the fluid is laminar. This is different to turbulent flow, which is when the layers of fluid cross into each other, resulting in the formation of vortices or eddy currents, causing an abrupt change in velocity. This means the sphere is not at terminal velocity, so it does not follow Stokes' law. Using the previous equations of upthrust plus viscous drag equals weight and Stokes' law, we can construct an equation for viscosity. As the density of the sphere is equal to its mass divided by its volume, the mass of the sphere is equal to its density times its volume. To find the weight of the sphere, you times its mass by the gravitational field strength. We can sub in density times volume for mass, so the weight of the sphere is equal to its density times its volume times the gravitational field strength. The volume of a sphere is found using the equation 4 over 3 pi r cubed, so we can sub that in for v to get an equation for the weight of the sphere as 4 over 3 pi r cubed times its density times the gravitational field strength. Upthrust is equal to the weight of the fluid displaced. Similar to the sphere, you can sub in the density equation for mass in the weight equation, so upthrust equals the density of the fluid times the volume of displaced fluid times the gravitational field strength. As the sphere is fully submerged in the fluid, the volume of fluid displaced is equal to the volume of the sphere, so we can sub in 4 over 3 pi r cubed for v to get an equation for the upthrust of the fluid as 4 over 3 pi r cubed times its density times the gravitational field strength. We can sub in the equations for the weight of the sphere and the upthrust into the equation weight equals upthrust plus viscous drag, so 4 over 3 pi r cubed times the density of the fluid times g plus 6 pi times viscosity times rv equals 4 over 3 pi r cubed times the density of the sphere times g. By minusing the upthrust from both sides and then dividing by 6 pi rv, we can make viscosity the subject. By factorising 4 over 3 pi r cubed g from the top half of the equation, we can get an equation for viscosity stating that it equals 4 over 3 pi r cubed g times, in brackets, the density of the sphere minus the density of the fluid, all over 6 pi rv. This can be simplified further by cancelling out the pi's and dividing the r cubed on the top by the r on the bottom, and then moving the 3 from 4 over 3 to the bottom half of the equation. Timesing 3 by 6 gives 18. This can be simplified further as 4 over 18 is equal to 2 over 9. This gives a final equation for viscosity as viscosity equals 2r squared g times in brackets the density of the sphere minus the density of the fluid all over 9V. I used this formula to measure the viscosity of bath soak. The equipment I used were 7 metal ball bearings, Radox bath soak, kitchen scales, a ruler, a long cylinder glass vase, a measuring jug, the stopwatch app on a phone, and another phone to play back the balls sinking in slow motion. Using kitchen scales, I found the mass of 7 metal balls as 125 grams. I divided this by 7 to get a mass of 0.0179 kilograms to 3 significant figures for a single ball. Using a ruler, I measured the diameter of one ball bearing as 1.6 centimeters, so the radius of each ball is 0.8 centimeters. To get the volume of a ball, I used the equation 4 over 3 pi r cubed, so 4 over 3 times pi times 0.008 cubic meters gives a volume of 2.14 times 10 to the minus 6 meters cubed to 3 significant figures. To find the density of a ball bearing, I divided its mass by its volume, so I divided 0.0179 kilograms by 2.14 times 10 to the minus 6 meters cubed to get a density of 8,330 kilograms per meter cubed to 3 significant figures. To find the density of the bath soak, I used the kitchen scales to measure the mass of an empty measuring jug. This gave a value of 565 grams. I then poured the bath soak into the measuring jug until it was about 3/4 full. This gave a mass of 938 grams. To get the mass of bath soak in the measuring jug, I subtracted the mass of the empty jug from the mass of the jug and the bath soak combined. This gave a mass of 0.373 kilograms. Finally, I used the measuring jug to measure the volume of bath soak inside it as 370 centimeters cubed, which is equal to 3.7 times 10 to the minus 4 meters cubed. I then divided the mass of the bath soak in the measuring jug by the volume in the measuring jug to get a density of 1010 kilograms per meter cubed to 3 significant figures. Then I stuck 2 pieces of tape to the long cylinder tube and poured the bath soak into it. I used a ruler and measured the distance between the tops of both the tapes as 0.1 meters. I then placed the stopwatch next to the cylinder and recorded both the stopwatch and the bath soak. I dropped a ball bearing into the bath soak and played back in slow motion so I could find the time it took for the ball to travel between the tops of the 2 tapes. I repeated this 4 more times and calculated the mean time of 0.248 seconds. I divided 0.1 meters by 0.248 seconds to get an average velocity for a ball bearing as 0.403 meters per second to 3 significant figures. I then put these values into the viscosity equation. So the viscosity of bath soak is 2 times 0.008 squared meters times 9.81 meters per second squared times, in brackets, 8,330 kilograms per meter cubed minus 1,010 kilograms per meter cubed all over 9 times 0.403 meters per second. This gave a viscosity of 2.53 Pascal seconds to 3 significant figures. To improve the accuracy of the experiment, I could use a micrometer instead of a ruler to measure the diameter of the ball bearing. I could also use a longer cylinder so the tapes are further apart, so the ball takes a greater time travelling between the 2 tapes. This could also allow for me to have a longer distance between the top of the fluid and the first tape, ensuring the ball reaches its terminal velocity before measuring its velocity. I could also use a digital balance instead of kitchen scales to get a more accurate value of mass. Finally, I could use a more viscous fluid such as honey or washing up liquid, so the ball takes a longer time travelling between the 2 tapes.